Hello, and welcome to our discussion of adjoints. We'll begin with an inner product space X and operators T and S in X. That is, we have subspaces D of T contained in X and D of S contained in X, such that T is a linear operator from D of T back into X, and S is also a linear operator from D of S back into X. And now we'll say that T and S are adjoint to each other if we have the following relation. If the inner product of TF against G is equal to the inner product of F against SG for all F in the domain of T and all G in the domain of S. That is, when I start out with the inner product TF on G, I can pop the operator T sort of over to G, but then T has to become S. And we'll also say that the operator T is self-adjoint or Hermitian if T is adjoint to itself, namely if the inner product of TF on F is equal to the inner product of F on TF for all F in the domain of T. So we'll do an example. Let's take a matrix A in the n by n complex numbers, and we'll define an operator M sub A on Cn by the following relation. M sub A on X will simply be A times X. So M sub A is just the matrix vector product caused by multiplication by A. And now let A star be the conjugate transpose of the vector A. So A star is also a vector in C, is also a matrix in C n by n. And then we have the following relation with the dot product. The product A times X, dot product that with Y, is equal to X, take the dot product of that with A star on Y for all vectors X and Y in Cn. So this tells us that M sub A is self-adjoint if and only if A star is equal to A, which happens if and only if A is a Hermitian matrix, going back to our linear algebra definitions. And otherwise, an adjoint for the operator M sub A is M sub A star. This should not be that surprising if we think about what Hermitian matrices and the dot product do in linear algebra in finite dimensions. Here's a bit more of a complicated example. Let's say I have a function f that goes from the real numbers into the complex numbers, so f is defined on all of R, and I'll define tf of x to be I times x times f of x. So now t is a linear operator, and t is defined right now for all functions f from the reals into the complex plane, but we're going to work with a much more restrictive subset of those functions. We'll look at the domain of t to be all f in L2 of R, such that the improper integral of the modulus of x times f of x also converges. Then the question is T self-adjoint with respect to the L2 inner product, which for us in this example will be inner product of fg on L2 is the integral from minus infinity to infinity of f of x times the complex conjugate of g. We've met this inner product on different intervals before, and now we're working with it on all of R. So let's take f and g in the domain of t, and let's calculate this inner product. Tf on g is equal to the integral from minus infinity to infinity of ix f of x times complex conjugate of g of x. And that's equal to the integral from minus infinity to infinity of f of x times the conjugate of minus ix g of x. So what did I do here? I started out with the conjugate on g of x, and I had this ix factor in front of f, and I'll move that ix factor under the conjugate by turning I into minus I, but x just gets to stay x because x is a real number. So the inner product tf against g in L2 is equal to the integral from minus infinity to infinity of f times the complex conjugate of minus ix g of x. And we see that, in general, it shouldn't be the inner product of f against tg. right? Because tg would just be ix g of x. Now we have a minus sign in here. However, the same calculation shows that an adjoint for t is sg on x defined to be minus ix g of x. Because if I look in the integral above and I replace minus ix g of x with sg of x, well then I have the adjoint relation right there. Here's a third example. Let's take x to be the continuous functions on the interval 0 to 1 into the complex plane. That'll be our vector space. And we'll define an operator t in x by t on f at x is f double prime of x, which is to say t is dx squared. And we'll let t have the domain in x to be all functions f and c2 with the following lengthy requirement. F of 0 is equal to f of 1 is equal to f prime of 0 is equal to f prime of 1 is equal to 0. So again, my ambient space x is all continuous functions on the interval 0 to 1, and the domain of my second derivative will be all twice differentiable functions on 0 to 1 that satisfy these sort of boundary conditions. And we'll let x have the L2 inner product. Inner product of f and g will be the integral from 0 to 1 of f of x times conjugate of g of x. So this is one of the many guises of the L2 inner product now on the closed bounded interval 0 to 1 instead of the whole real line as above. And we'll ask ourselves, is t self-adjoint? So let's integrate by parts twice. We start out calculating inner product of tf against g. That's the integral from 0 to 1 f double prime of x conjugate g of x. So we'll integrate by parts here. This will be f prime of x conjugate g of x evaluated at x equals 1, and then subtract from that the evaluation at x equals 0, minus the integral from 0 to 1 f prime of x conjugate g prime of x. And hit pause if you need to calculate that out. Remember, we can do integration by parts with complex valued functions and conjugates just as with real valued functions. So these boundary terms, the f prime of x and g of x bar, they all vanish because f prime of 1 is 0, and so is f prime of 0. And the same thing for g, because f and g are both in the domain of t. So I'm left now with this integral minus integral 0 to 1 f prime of x conjugate g prime of x. Let's integrate by parts again. This becomes minus f of x conjugate g prime of x evaluated and subtracted from x equals 0 to x equals 1 plus the integral from 0 to 1 f of x conjugate g double prime of x. And I like that last integral a lot. And once again, we'll see the boundary terms minus f of x conjugate g prime of x vanish because, again, f of 0 is equal to 0, f of 1 is equal to 0, and the same thing for g. So the whole thing just turns into the integral from 0 to 1 of f of x times the conjugate of g double prime of x, and that, of course, is equal to f inner producted with tg, so t is self-adjoint. And the important thing here was not just that t was the differential operator, take the second derivative, but that we allowed it to have the domain with all those nice boundary conditions that forced the boundary terms on integration by parts to become 0. That was critical to making t self-adjoint. Here's one of the reasons we like self-adjoint operators so much. Suppose that t is self-adjoint on an inner product space x, then every eigenvalue of t is a real number. Let's prove this. So we'll start out with the usual eigenvalue-eigenvector relation. We have tf equals lambda f for some lambda in the complex plane, and some f that is a non-zero vector in x, really a non-zero vector in the domain of t. T doesn't have to be defined on all of x. And I'm starting out with lambda being complex, and I want to end up forcing lambda to be real. So how can we use self-adjointness here to tell us something about lambda? And the answer is a bit of trickery. Say we start out computing the inner product lambda times f against f. There's no reason we really should do this, but it's the right thing to do. Well, this is the inner product of TF with F, because lambda F is equal to TF. And now I'm going to move that T over to the other element of the inner product, and I can do that because T is self-adjoint. So inner product of TF with F is inner product of F with TF. And that's inner product of F with lambda F, again using the equality TF equals lambda F. And now I'm going to flip the order of the elements in my inner product around. This is the conjugate of lambda F inner producted with F, just by properties of the inner product. And now I'm going to pull out a factor of lambda. This will be conjugate lambda times conjugate of F with F. Again, I'm using properties of the inner product to pull that lambda out, and properties of multiplication of complex numbers to split up the conjugates. And this is conjugate of lambda times the inner product of F with F. Okay, so now I see on the way far left side a lambda, and on the far right side a lambda bar. That's optimistic. Remember, though, that the inner product of F with F is the square of the norm induced by the inner product, and this is always a positive real number because F, we assumed, was not the zero vector. So what do I see? From the right side, I have lambda bar norm F squared is equal to lambda bar times inner product of F with F. That's my left side above rewritten. But that's lambda F inner producted with F, or just lambda inner product times inner product of F with F, and that's lambda times the norm of F squared. So what do I get out of this chain of equalities? Lambda bar times norm of F squared equals lambda times norm of F squared. And then I can divide, since norm of F squared is non-zero, to get lambda bar equals lambda. And so if I have a complex number lambda, and its conjugate lambda bar is equal to the original lambda, that lambda must be real. And so I've shown that every eigenvalue of t is indeed real. One bit of awkward mathematical phrasing here. I didn't really say that t has to have eigenvalues. Remember, we saw operators that didn't have eigenvalues on infinite dimensional spaces. Kind of awkward when we think about finite dimensional matrix operators. So really what we're saying here, and this is sort of buried in the mathematical phrasing, if t has an eigenvalue, then that eigenvalue has to be real. We will not enter into proofs of whether or not t has eigenvalues to begin with. Another happy fact, assuming that we have some eigenvalues to play with, eigenvectors of t corresponding to distinct eigenvalues are orthogonal. By this, I mean if tf equals lambda f, and if tg equals mu g, and lambda is not equal to mu, here lambda and mu are complex scalars, necessarily now real scalars, and f and g are vectors in the domain of t, then the inner product of f with g must be 0. So again, we'll do a little trickery. First, we need to remember that we have proved that lambda and mu must be real numbers because they're eigenvalues. And we'll start out doing sort of a similar computation. Say we take the inner product of lambda f and g. This is the inner product of tf with g, because lambda is an eigenvalue for t. This is the inner product of f with tg, because t is self-adjoint, so I can pop it from one side of the inner product to the other. This is now the inner product of f times mu g, because mu is an eigenvalue for t with eigenvector g. And now I'll flip the order around and take the conjugate. This is conjugate of the inner product mu g on f. I'll pull out a factor of mu. This is conjugate of mu times conjugate of the inner product g with f. Mu is real, so conjugate of mu is mu. And then conjugate of inner product g with f is just inner product of f with g. You can flip the order around and remove the conjugate. And so I have to have now, if I subtract these two things, 0 is equal to mu times the inner product of f with g, minus the inner product of lambda f with g. And that, of course, is mu times the inner product of f with g minus lambda times the inner product of f with g. I've pulled lambda out. So that's mu minus lambda times the inner product of f with g. And we assumed from the start that mu and lambda were distinct eigenvalues of t, so mu minus lambda is not 0, and therefore we can divide by mu minus lambda to get the inner product of f with g equals 0. Again, we didn't prove that this particular self-adjoint operator had eigenvalues. We just said if it does, and if it has two distinct eigenvalues, then the corresponding eigenvectors must be orthogonal.